In the vast expanse of the universe, where galaxies drift like luminous islands in a dark sea, mysteries abound. Among these, one of the most tantalizing questions concerns our own home, the Milky Way galaxy. How did it come to be? What ancient forces shaped its form and guided its evolution? Today, we'll dive deep into the cosmic origins of our galaxy, tracing its journey from primordial chaos to the spiral haven we now call home. The birth of the Milky Way. The story of the Milky Way begins over 13 billion years ago, during a period known as the Cosmic Dawn. This was a transformative era in the universe's history, marked by the emergence of the first light after the cosmic dark ages. In the aftermath of the Big Bang, the universe expanded and cooled, allowing the formation of simple atoms, primarily hydrogen and helium. These primordial elements formed vast, diffuse clouds that began to coalesce under the influence of gravity. Within these clouds, pockets of higher density emerged, collapsing further to ignite the first stars. These stars, known as population 3 stars, were unlike anything that exists today. Lacking heavier elements, they were composed almost entirely of hydrogen and helium, making them enormous, hot, and short-lived. Their intense radiation ionized the surrounding gas, carving out pockets of transparency in the opaque universe. When they ended their lives in spectacular supernova explosions, they enriched the surrounding medium with heavier elements, setting the stage for the next generations of stars and the formation of galaxies. During this epoch, gravitational forces began to sculpt the large-scale structure of the cosmos. Dark matter, the enigmatic substance that makes up much of the universe's mass, played a pivotal role. It gathered into vast halos, creating the scaffolding upon which galaxies would form. Ordinary matter, gas and dust, was drawn into these halos, accumulating in their centers. In one such halo, a dense region of gas began to rotate and collapse, giving birth to the first structures that would evolve into the Milky Way. The universe was still young, having emerged from the Big Bang a mere 400 million years earlier. In this era, the first stars began to ignite, forming in dense regions of primordial hydrogen and helium gas. These early stars, known as population 3 stars, were massive and short-lived, burning through their nuclear fuel at a furious rate. When they died, they exploded in supernovae, seeding the surrounding space with heavier elements, carbon, oxygen, and iron, necessary for future star and planet formation. Around this time, gravitational forces began to weave the fabric of what would become galaxies, initiating a cosmic ballet that defined the structure of the universe as we know it. These forces worked over vast timescales, pulling together clumps of dark matter and ordinary matter into regions of higher density. Within these dense regions, gas and dust began to spiral inward, driven by the relentless pull of gravity. The process was not uniform. Turbulence and instabilities in the gas created ripples and eddies, which influenced the eventual shape and composition of the forming galaxies. Gravitational interactions between proto-galaxies and smaller satellites further amplified the complexity of this structure, setting the stage for the intricate galactic forms we observe today. Dark matter, the mysterious and invisible substance that makes up about 27% of the universe, played a crucial role in the formation and evolution of the Milky Way. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it detectable only through its gravitational effects. This elusive substance formed vast halos that acted as the gravitational scaffolding for galaxy formation. Within these halos, its gravitational pull gathered ordinary matter, gas and dust, into dense regions where stars and clusters eventually began to form. While its exact nature remains one of the greatest mysteries in modern physics, simulations suggest that dark matter's distribution was a key factor in shaping the large-scale structure of the universe. By creating potential wells deep enough to hold vast quantities of gas, it set the stage for the intricate cosmic architecture we observe today. The interactions between dark matter and baryonic matter also influence the rotation curves of galaxies, contributing to their stability and the preservation of their spiral shapes over billions of years. The invisible hand of dark matter continues to guide the evolution of galaxies, subtly steering their dynamics and interactions on a cosmic scale. Dark matter formed vast halos, whose gravitational pull attracted ordinary matter, gas, and dust. Within one such halo, a swirling maelstrom of gas began to coalesce. This was the seed of our Milky Way, building blocks, the formation of stars and clusters. As gas collapsed under gravity, it fragmented into smaller clumps, each forming stars. These stars grouped together in clusters, some of which survive to this day as globular clusters orbiting the Milky Way's core. Over time, the growing galaxy absorbed smaller proto-galaxies through a series of cosmic mergers. Each merger added mass and stirred the galaxy's structure, contributing to its eventual spiral shape. One of the most significant mergers occurred around 10 billion years ago, involving a smaller galaxy dubbed Gaia Enceladus. This collision not only added a substantial number of stars, but also shaped the Milky Way's thick disk, a component that lies between the central bulge and the thin disk where the spiral arms reside. The role of the supermassive black hole. At the heart of the Milky Way lies Sagittarius A, a supermassive black hole with a mass equivalent to about 4 million suns. This black hole has been a silent architect of the galaxy's evolution. While it rarely consumes significant amounts of material today, its past activity likely influenced the distribution of stars and gas in the central bulge. Energetic outbursts from Sagittarius A star may have driven powerful winds, clearing out gas and regulating star formation in the core. Spiral arms, the Milky Way's signature. The iconic spiral arms of the Milky Way began to take shape around 6 billion years ago. These arms are not static structures, but rather regions of higher density within the galactic disk. As gas and stars move through these density waves, they compress, triggering bursts of star formation. This process explains why the arms appear so bright and populated with young blue stars. The arms also host vast molecular clouds, nurseries where new stars are born. Our own sun emerged from one such region about 4.6 billion years ago, accompanied by a retinue of planets, moons, and other celestial bodies. The sun's location within the Orion arm, a minor spiral arm, offers a relatively quiet and stable environment, shielding Earth from the chaotic activity near the galactic core. Cosmic cannibalism. The Milky Way's hunger galaxies grow by consuming smaller galaxies, and the Milky Way is no exception. Even today, it continues to absorb its neighbors. The Sagittarius dwarf galaxy, for instance, is currently being torn apart and assimilated into the Milky Way. These interactions not only add stars, but also redistribute gas and dark matter, profoundly altering the galaxy's morphology and internal dynamics. When smaller galaxies are consumed, their stars often form tidal streams, graceful arcs that stretch across the galaxy's halo. These streams provide astronomers with a living record of past encounters, each a snapshot of cosmic cannibalism in action. Additionally, the redistribution of gas can ignite new waves of star formation, breathing fresh life into the galactic disk. The gravitational interplay during these mergers also injects kinetic energy into the system, potentially reshaping spiral arms and thickening the galactic disk. Over billions of years, these processes combine to sculpt the Milky Way's distinctive appearance, creating a cosmic tapestry woven from the remnants of countless galactic interactions. One of the most dramatic future events in the Milky Way's story will be its collision with the Andromeda galaxy, scheduled to occur in about 4.5 billion years. This titanic merger will reshape both galaxies, likely forming a new elliptical galaxy dubbed Milkomeda. While this may sound catastrophic, the vast distances between stars mean that actual collisions between them will be rare. Mapping the Milky Way, modern discoveries. Understanding the Milky Way's structure and history is a monumental task, given that we are embedded within it. However, advances in astronomy have allowed us to piece together a detailed picture. Observatories like the European Space Agency's Gaia mission have mapped the positions and motions of over 1 billion stars, revealing the galaxy's intricate dance. Gaia has also uncovered evidence of past mergers, such as streams of stars left behind by devoured galaxies. For instance, the Sagittarius stream, a prominent stellar stream, provides direct evidence of the Milky Way's ongoing consumption of the Sagittarius dwarf galaxy. These streams, composed of stars ripped from smaller galaxies, arc gracefully through the Milky Way's halo, tracing the paths of ancient interactions. The Helmi stream, another example, tells the tale of a long-lost galaxy that merged with the Milky Way billions of years ago. By studying the chemical composition and motion of these stellar streams, astronomers can piece together the timeline and nature of these cosmic collisions, shedding light on the complex and tumultuous history of our galaxy's growth. These stellar streams act as fossils, preserving the memory of the Milky Way's tumultuous past. By studying them, astronomers can reconstruct the timeline of our galaxy's growth. The Milky Way and life. One of the most profound aspects of the Milky Way's story is its role in fostering life. The elements forged in ancient stars and spread by supernovae provided the raw materials for planets like Earth. The galaxy's structure, particularly its relatively calm spiral arms, created stable environments where life could take root and evolve. Our position within the galaxy is also significant. Located about 27,000 light-years from the galactic center, Earth resides in the so-called Galactic habitable zone. This region balances the risks and resources necessary for life. Closer to the core, intense radiation and gravitational forces would make life difficult. Farther out, a scarcity of heavy elements might hinder planet formation. The future of the Milky Way. The Milky Way's story is far from over. As it continues to evolve, new stars will be born, and old ones will fade away. The galaxy's spiral structure may change, influenced by ongoing mergers and interactions with satellite galaxies. The eventual collision with Andromeda will mark a new chapter, creating a galaxy that is both familiar and utterly transformed. On a cosmic timescale, the Milky Way is just one of countless galaxies, each with its own unique story. Yet, for us, it is home, a cradle of stars and planets that has nurtured life and inspired countless generations to look up and wonder. Its journey from a primordial cloud of gas to a majestic spiral is a testament to the power of gravity, the resilience of matter, and the unyielding march of time. As we continue to explore the universe, the Milky Way serves as a reminder of our place in the cosmos. It is a bridge between the infinitesimal and the infinite, a beacon of light in the vast darkness, and a testament to the beauty and complexity of the universe we inhabit. Thank you for joining us on this incredible journey through space and time. If you enjoyed this exploration, please like, subscribe, and hit the notification bell to stay updated on all our cosmic adventures. Share your thoughts in the comments below. What fascinates you most about the Milky Way? Until next time, keep looking up and keep wondering.